All right. I'm Lin Tan. Can everyone hear me?
Yes.
Good. So now I'm the only one between you and lunch. So my goal is to finish in 20 minutes or even 18. So I give it a really big title, but I'm really going to focus mostly on one piece of our recent work and then just summarize a lot of our projects very quickly, kind of to talk about what we can do with the synergy between artificial intelligence and software. So as many of you know, even from decades ago, we start already applying a lot of machine learning and natural language processing techniques to address software development challenges. For example, to build models to find and fix bugs, to detect malware, to analyze software checks, et cetera, even to automate some of the processes. But on the other hand, we can use software techniques such as testing verification to improve the overall reliability and security of the AI systems. And this is getting ever increasingly so important as those AI systems become almost every part of our life. They're at our home, self-driving cars, people use to diagnose Alzheimer's disease, use it to compose music, etc. So it's really, we need those systems to be correct, to be secure. And these AI systems consist of two major components. The models, the algorithms, the complex math that we have already heard about a lot of talk about. But there's also the other part, that's the software implementation. Ultimately, those models, the algorithms need to be implemented. The model has to be loaded in software. And the software system has to be correct as well, the whole system to be correct. And so far, most of the effort has been focused on making sure the models, the algorithms are accurate. But as we have seen, there are actually a lot of challenges and differences of the defects and the bugs in those AI software implementations. They are written by us. We're human. We make mistakes just like any other software. They contain bugs and security vulnerabilities. And a lot of them are different than the bugs in the traditional systems. So really need new support and new help here. So we're going to talk about Cradle. That's kind of one of the first kind of highlight the importance of testing the software implementation of those AI systems, in particular deep learning systems. And those are very difficult to test. Think about how you normally test a piece of software. If you're calculating 1 + 1, you give that as input to the program, see, do you see 2, right? You know the expected output, see if the program gives the expected output. And that's very difficult for a lot of the AI system, particularly deep learning system. They have very complex math, and that's in some sense, I'm not doing it, I'm letting the model to figure it out. So I don't know the expected output of that complex calculation. So it's very difficult for us to test those type of systems. And some might say, well, maybe I can use what we call the ground truth. So here I'm showing a picture of bananas. I mean, I may not know for a particular model what the math calculation should be, how it's doing. If we're doing image classification, I know the ground truth. It should be bananas. I just expect my system to tell me that those are bananas, and I declare success. The system is good. But that's not enough. So here I'm showing a model called MobileNet V2, and I'm letting TensorFlow run the system. It gives me bananas. All good? But then we just missed two important bugs. One in the model, because most models are not 100% accurate. And this is one of the few examples it's making a mistake. So if you base on the math calculation, it's supposed to tell you it's a tennis ball. And there is a bug in the software implementation of the TensorFlow library backend. And this bug somehow kind of cancel out on this image. So if we just test the whole thing, expect to get the ground truth, we just miss both bugs. So this just highlight kind of the importance. We really need to test the two parts separately, and there's already a lot of effort on the model. So this talk I'm going to focus on how do we test the software implementation given the challenges of the software implementing deep learning systems. All right, so I don't know the expected output. and I'm not really trying to figure that out. What can I do? Guess. We can do a little better than that. How about something similar to differential testing? So I don't know what the model is supposed to do given an image, but luckily, there are plenty of implementations of the same algorithms. There's at least 20 open source packages implementing RN and CNN. I'm going to load 2 of them, let's say. The same model, same network, the same weight, different software implementation. Given an image, could be anything. Now we're using Petri dish here. And here, I don't need to know what the expected output is. I don't even need to know what the ground truth is. What I need to know is, are they consistent? If these 2 models give me, sorry, I think it's just hard to see, give me different output, then I know they can't both be correct. So that gives me enough evidence to go back to the developers and understand the bug and report the bug and help them debug and fix the bug. Now, that's kind of the basic principle. It's a very powerful technique. It's been used in different areas, and this is applying here for deep learning challenges, for deep learning software. But that has challenges. Okay. Before we get there, and this is a real bug. I just want to show this is the one we found in the CNDK backend, and we reported it has been fixed. And it's essentially, we're supposed to take the square root of the variable plus epsilon, but the brackets were misplaced. Okay. So the idea is simple, but there are challenges. So first of all, we're running this with floating point calculation on GPUs and different hardware. If you just expect the raw output, they would be different, running on different hardware with different software implementations. So we have to be a little smarter and figure out what is the natural variation in the calculation and what differences lead to our indications of possible defects and bugs in systems. And as that, so our work Cradle would essentially run 2 implementations to extract the output, compare them. And if one of the systems crashed, that's in a sense an easier bug. If something crashes, we know it's a bug. If it's not, then we go ahead and compare the differences. Eventually, we'll localize the bug to the particular layers. Let's look at the detection phase first. So we propose 2 kind of metrics to measure what differences are important for different types of tasks. One's for classification, the other's for regressions. I'll give you the time, and we're just going to explain a little bit how the classification works. Although I explained the ground truth may not be the only good indicator to detect the bugs in the software implementations, it can help. So here, instead of looking at the raw differences, we use the label to calculate the differences, because ultimately, if the raw calculation doesn't lead to different labels, it may not be important enough for the users. So here, we look at if, for example, the common top 5 labels, if they're different, and we want to give them different weight if you have the ground truth at the top 1 versus the top 2. So calculation to look at, example, if you got the ground truth at the top 1 label, you get weight T. If it's the number 2, it's weight 8. And for the CNT example, it's because the top 5 does not contain the correct label, it got 0, the difference is 16. So that's how we kind of measure the differences on an image. Then we have a way to aggregate all these on thousands of images, not only help us detect the differences, but also to kind of cluster to find unique inconsistencies. Because as you will see, the bugs are in the software itself, but you can have thousands of images or multiple models to trigger the same bug in the software. So we need actually a way to kind of a cluster to identify the unique inconsistencies. All right. So that's kind of very quick way of going through that. The next step is a very important challenge. Once I know there's a failure in the system output different labels, how do I figure out which layers potentially are responsible for these differences. So what we would do is we have two, go through roughly the same execution graph, they execute the same functions. Then we can just take the differences. So on the top is one model, and the bottom is another model. And then we can take the differences and calculate how much difference there is, and then we find a way to look for the biggest jump from different layers. Of course, we normalize that. This is of course, it's some sort of heuristic to kind of give a hint which layer potentially responsible. And in this example, I've showed the batch normalization, which is the same like I showed, did point out to the root cause function. All right, and this is quite important because you can see those execution have over 700 layers. So for human, it also helped us tremendously when we report those bugs to developers because it helped us have some confidence what the bugs we found is. All right, so we did this with 3 backend, TensorFlow, CNTK, and Theano with 28 models, 11 data sets, and we also tried multiple versions of the backends. And we found 12 bugs, 5 of them are crash bugs, 7 are inconsistency bugs. Now here I'm just want to show that we're not talking about which particular library is buggier than others. We found bugs in all of them, which just shows it's a general challenge. They are software, they contain bugs, we need support. We need more and more support along this. And I'm very happy recently heard that Microsoft is trying this out, implemented it internally to see how well this works. All right, so with the 3 libraries we found with the open source, we found 12 bugs and reported them. 3 of them are new, previous unknown bugs, and most of them has been fixed since then. All right, so that's kind of testing, and we clearly need to do more along this line, but now I'm gonna kind of flip to the other side, what we can do to use machine learning techniques to help improve software tasks. How do we automate some of these tasks? Developers spend a lot of time on fixing bugs. Can we help automate that processes that can improve engineering productivity, that can help us improve software dependability? So one theme here is software text analytics. Now in the Cradle, I talked about how do we find inconsistencies between 2 implementations. Now, what about the text? Here are the comments, documentation, user manuals. So we're just bringing another source of information. You can look for inconsistencies between the source code and the software text. So here is an example that is a piece of code on the top. If you look at the green line, is the code in Linux kernel saying the caller of the function is responsible for calling a log, and at the bottom, we check the entire call chain, no log was held. That's clear inconsistency. And of course, I don't know, is the bug or the comment is wrong? In this case, it was a bug in the source code, and we reported that to the developers, confirmed that's indeed a bug in the source code. Right? So the point here, again, we're applying inconsistent checking of 2 sources. Now, instead of checking between source code, we're looking at source code and the code comment. And in this case, we applied, of course, machine learning, supervised learning, natural language processing to analyze the text, because that's, in a natural language, have challenges. And this is an example of where now we can do the same with a dynamic testing. Instead of statically generate test cases, the comment that, well, the parameter should not be null, meaning that if you give null, you're supposed to throw exceptions. So we generate a test case, call that function, pass null as parameter automatically by analyzing comment, java.comment, and generate a JUnit test using the Randoop testing framework. And then we're able to find this bug, and in this case, we have reported, developers have confirmed that and fixed it. All right, so this is sort of, we can looking for inconsistencies, but the power of analyzing and leveraging the software text is beyond inconsistent checking. We can actually extract information from the source code and use that to guide our test approaches. So typically when we do testing, we have a lot of execution paths to test. Given one branch, we have 2 execution paths coming out of it, so we have the typical state explosion problem. And symbolic execution has been very effective if you systematically go through those paths, but it still suffers from the state explosion. You still have to decide what's the next state you're going to explore. So based on that, use document to say, hey, I can use document. I know what input are valid, what input are important. I'm use that to guide my symbolic execution, and we showed that could help. Essentially, analogy here is if you have a maze, you have to go through. I don't know how, but if I can tell you this blue path or dead is useless, based on whatever information I can get from history, from document, you can go through, find the actual path from entry to exit much faster. Okay? And we can also have more ambitious goal. We're going to build a machine learning model from history of millions of bugs, just try to find bugs and fix bugs automatically. I've done some of this initial work there as well. All right, so I just want to thank all my students who have contributed some of this work, and thank you.